As you know, species have to respond to climate change or they will face extinction. And on the long term, they can only do so by genetic adaptation. Classically, this is a change in the means, for example, bud burst or mean diapause timing. But we've seen also a lot of examples today that plasticity may evolve. And this has received a lot of attention recently because plasticity changes how selection can act and may change the speed of responding to to climate change. But there's actually a third one, a third and fourth strategy that is bed hedging strategies, and they received a much less attention in the face of a changing climate. And that's a bit surprising because it's about coping with predictability or changing predictabilities. Like, for example, this desert plant, it's impossible to predict whether the next year will be rainy or will be a drought year. And so the best plasticity can't work here. And the best strategy is maybe to spread your risk and produce both seeds that germinate and some that stay inside the soil for another year. So that not all seeds get die in a bad year. So in general, diversified bed hedging means increasing the variance in your offspring so that you decrease the long-term fitness variance. I think these different modes of genetic adaptation are sort of overlapping and interacting, and I want to tear them a bit apart and say how they can help in a changing climate. I first will provide a common framework. You can find it here on the preprint server. Essentially, I have trouble with separating phenotypic plasticity and diversified bed hedging. Because if you go back to this example, clearly a bed hedging example, because it's about offspring fitness variance. You could also say, take the mother's perspective and say, well, the mother made a choice between two phenotypes, so it's also plasticity, right? Well, not exactly, because it's just because there's variation in phenotypes, it does not mean that there is phenotypic plasticity involved. And I want to go on with that a bit. The key word here is having a choice. Both plasticity and diversified bed hedging mean that there is a decision process involved. It's about using winged or wingless offspring, or should I continue development or stop development. So we can maybe display it as a polyphenic reaction norm. And a polyphenic reaction norm has on the y-axis, a probability. We can say the main feature of a reaction norm is that the probability changes with the environment, or in other words, that there is variance among environments. Here is a typical bed hedging reaction norm. Here, both phenotypes are expressed, and there's no change with the environments. But that does not mean that there is no variance involved. It's just no variance among environments, but it is within each environment, because there is a variance among the offspring. So because we are talking about probabilities, this is essentially the variance can be described as a Bernoulli draw, or the variance of a Bernoulli draw. We can mix these two reaction norms. You get something like this, with less range and a flatter slope. So a bit of the variance among environments is now given up in favor of variance within environments. So I would like to define the variance composition, which is just the ratio of the two variances. Then we can have such a reaction norm, well, not a reaction norm, because there's no change at all, it's just one phenotype being expressed. That's classical canalization. Canalization is the opposite of phenotypic plasticity, but it's also the opposite of bed hedging reaction norms. Or in general, it's the opposite of phenotypic variance, which I define as the sum of the two variance components. And I find that important because it means we should not be talking about the role of plasticity in evolution, but the role of phenotypic variance in evolution, which may be either variance among or within. So either bed hedging or plasticity. Last term I would like to define is strategy, evolutionary strategy. I would say it's a reaction norm shape that is adaptive in a given environment. So it has provide a fitness benefit in an environment. So when we talk about reaction norms, we should talk about variances, variance components of phenotypic variance, but not about bed hedging and plasticity. I want to talk a bit more about the strategies. Here you see 9 reaction norms sorted on the x-axis by the variance component, so high variance among, low variance among, and instead variance within environments. And on the y-axis is here canalized reaction norms, and here those with high phenotypic variance. I would expect that the ratio correlates, so the x-axis correlates with environmental predictability. So highly predictable environments select for high variance among, and I call that resulting strategy phenotypic plasticity. On the other hand, low environmental predictability should select for bad hedging, diversified bad hedging. So these two form a continuum of strategies, and I call that the information axis. The y-axis is should correlate with the amplitude, because high canalization, so here, should not occur in an environment that doesn't change, and these should instead occur there. So that I call the responsiveness axis, going from fixed to flexible phenotypes. Then there's a last axis I did not mention before, because also the mean can change. Generally, we would expect that the mean phenotype is correlated to the mean environment, so that the arithmetic mean is optimized. But in a highly unpredictable environment, we could also have conservative bad hedging, so that's now three-dimensional, that the mean is shifted. I call this axis a variance avoidance axis. So to sum up, there's a three-dimensional continuum of reactional shapes, consisting of phenotypic variance, variance composition, and the mean. And then there's an environment that changes in amplitude, predictability, and mean. And the environment should impose selection pressure on the reactional shapes, so that we get a three-dimensional fitness landscape. And so that should select for a certain strategy, which we can describe along these 3 dimensions: responsiveness, information use, or bad hedging versus plasticity, and variance avoidance, or arithmetic mean versus conservative bad hedging. From here, I would like to go on to the actual meta-analysis I promised. I want to see whether these strategies really exist, so whether the environment is correlated with reactional shapes. I took insect diapause as an example, because there's a lot of studies on that, and they generally look like this. Several populations are sampled from the environment, put under multiple day lengths, and the diapause incidence is recorded. So we get, in this study, 10 reactionals from 10 different populations. I found a total of 57 such studies with almost 450 reaction norms, and I correlated the mean, or the inflection point, with mean winter onset. As climate data, I took the GHCN data set, which has a lot of data. Each pixel here is one climate station, and I correlated the mean diapause of the populations with the mean winter onset rate of curves. Then I calculated the predictability of the winter onset, which is just the standard deviation of winter onsets, and I correlated it with the variance composition. Lastly, to test for conservative bad hedging, I tested whether the predictability correlates with mean diapause that's not yet explained by this model, so the residuals of this model. Okay, to the results. First, the mean phenotypology versus winter onset. What you can see here is mainly that there's just 3 colors involved. These 3 colors say that there's almost all reliable data comes from flies, butterflies, and mites. And well, the main point is that there is a correlation. So the arithmetic mean is optimized, but the correlation is quite low. And the low correlation comes mostly from these populations from high latitudes and early winter onset. We should actually expect them to be somewhere down here, so that the slope is 1-on-1. So the populations from very high latitudes and early winter onsets don't seem to track winter onset very well. The second part is about the information use axis, which is here you can see the variance composition is generally high, so a lot of steep curves, but there are also a few flatter reaction norms, so I can correlate it with winter predictability. I found a very weak correlation only, so very little evidence for diversified bad hedging. For conservative bad hedging, it's even clearer. The residuals in mean diapause timing don't correlate with predictability. So I find very little empirical evidence for bad hedging strategies here. To conclude, diversified bad hedging and plasticity form a continuum of strategies. Sorry, stopping. Oh, okay. Both contribute to phenotypic variance, and the results I just said for from the meta-analysis. So we are over time.
Yeah, please.
Sorry.
You have plenty of time for questions.
Oh, there's some questions there. I thought it was okay. Yeah.
So a lot of insects use a combination or a hierarchical combination of photoperiod and temperature cues for diapause induction.
Yes.
Were you able to subtract out ones where we know
There
that
is
there's
very
no temperature
little
effects?
studies that study multiple populations from multiple day lengths and multiple temperatures. So we cannot have that. But what I do have is a temperature predictability. I recorded this, and very indirectly, there should be a negative correlation. So I explained in the page part. So that's a bit why I can't explain negatively personally. By the way, I have it on GitHub, a preliminary draft of that. Same name as my business.
So how do you explain?
Yeah. Sorry, if you are going into your time,
You can ask a question.
Yeah.
So how do you explain the fact that you find so little hedging strategy?
One way could be by hyperplasticity, so a steep reaction on, even though there's so actually I don't think so, because it would be a steep reaction onto something else. I have to think a bit about it. But the only thing I can actually explain is maybe by bad hedging in time, in space instead of time, so dispersal, or bad hedging in identity for some species that they change their mode of mating. Otherwise, hard to explain.